All right, let's get into it. When we build the digital services we use every day, social media, online banking, you name it, we're always wrestling with a huge trade-off. We want our systems to be correct, but we also want them to be available all the time. And as we're about to see, you can't always have it all.
And this quote from Jay Krebs, man, it just hits the nail on the head. This is the central dilemma. In what we call distributed systems, where services are spread out across tons of different computers, things are going to go wrong. It's just a fact. Networks fail, servers crash. So what do? Do you stay online and risk showing someone the wrong information? Or do you shut down to make sure you're always 100% right? That's the choice we're digging into.
So, where does this problem even come from? Well, to make sure your data is safe, most databases keep multiple copies of it. But that creates a new problem. For a little while, those copies can get out of sync. One might have newer data than another. This whole idea is called eventual consistency.
But let's really look at that definition. Eventually is a super slippery word, right? It doesn't promise when. The data might sync up in a split second, or it could take minutes. For us as users, and for the developers building these apps, this is so confusing. I mean, have you ever updated your profile picture, hit refresh, and the old one is still there? Yeah, that's eventual consistency. And it just feels broken. It goes against everything we think we know about how computers should work.
So, what's the dream scenario? The absolute ideal solution would be a system that gives us the illusion that there's only one single master copy of the data. No matter who you are or where you are, you'd see the exact same thing as everyone else, at the exact same time. All those weird, confusing inconsistencies would just disappear.
And that dream actually has a name. It's called linearizability. You'll also hear it called strong consistency. And what it really is a recency guarantee. Here's the key takeaway. Once a write operation completes, any read that comes after it, from any person anywhere, must see that new value. It's a promise that you will always see the most up-to-date version of the data. No exceptions.
This diagram is a fantastic example of what happens when a system is not linearizable. So let's walk through it. A referee updates the final score of a game. Alice's app gets that update right away. She sees the game is over. So she turns to her friend Bob and tells him the final score. Bob, who hears this from Alice, then refreshes his own app. But his app is connected to a different server that's lagging behind, so his screen still says the game is in progress. He knows for a fact that his data is stale because he got newer information from a totally different channel, Alice's voice. This is exactly the kind of frustrating experience that linearizability is meant to prevent. So, to pull off this one-copy illusion, systems have to play by some really strict rules about timing. It's all about making sure that recency guarantee we just talked about is never, ever broken.
Let's look at this timing diagram. Time moves from left to right, pretty simple. Down at the bottom we have a client, client C, that's trying to write the value 1. At the same time, clients A and B are both trying to read the value. Because their read operations overlap with that write operation, the system has a little bit of wiggle room. It could show them the old value, 0, or it could show them the new value, 1. In that little window of uncertainty, either answer is considered correct.
But here's where the rules get super strict. In this scenario, client A does a read and gets back the new value 1. Now the cat's out of the bag. Notice that client B's read request starts after client A's read is already finished. That timing is everything. Because of that, the system must also show the new value 1 to client B. Once one person has seen the new reality, everyone who asks after that has to see it too. The timeline can't go backward.
Okay, so now let's look at a clear-cut violation. This diagram's a bit busy, but just focus on the last two operations on the right. First, client A reads the value and gets back 4. Then, a split second later, client B asks for the same value, but it gets back 2. Whoa, hold on. That's a major no-no. Since A's read finished before B's even started, B should have seen 4 or something even newer. Getting an older value is like time traveling backward, and that is just not allowed in a linearizable system.
It's really easy to get linearizability mixed up with another fancy term, serializability. So let's clear this up. Serializability is all about transactions, groups of operations that have to happen together. Think about a bank transfer. You debit one account and you credit another. Serializability makes sure it all happens as one atomic step. Linearizability is way simpler. It's just about the recency of a single piece of data. Like when you're grabbing a username, it makes sure that once that name is taken, it immediately looks taken to everybody else.
So, linearizability sounds pretty amazing, right?
It makes everything predictable and simple. But, as you might have guessed, this kind of perfection comes at a pretty steep price. There are some serious trade-offs involved.
So, when do you absolutely, positively need this level of perfection? Well, think about a database trying to elect a single leader. Everyone has to agree on who's in charge. Or a distributed lock, where only one computer can have the key at a time. But maybe the most relatable example is just registering a unique username. You need one single authoritative source of truth that can say, sorry, that name's already gone.
So let's talk about that classic trade-off. Imagine you've got two data centers running your service, and then, boom, the network cable connecting them gets cut. They're what we call partitioned. They just can't talk to each other anymore. So what does the system do?
And this brings us to the famous CAP theorem. What it says is that during a network partition, like the one we just saw, you have a choice. You can choose consistency, which in this case means linearizability, by basically refusing to answer any questions you can't be sure are 100% correct. But that means you become unavailable. Or you can choose availability, staying online but risking serving up some stale data. You can't have both.
But you know, a lot of experts today argue that the CAP theorem can be a little oversimplified. A network partition isn't really a choice you get to make, it's a failure that happens to you. A better way to think about it is that when a failure happens, you have to decide what to prioritize. The whole pick 2 out of 3 thing can be kind of misleading. And here's maybe the most important takeaway about the cost. It isn't just felt when something breaks. To guarantee you always have the most recent data, a linearizable system has to do a lot of coordination across the network, and network speeds are never perfect. So that coordination makes the system slower all the time, even when everything is running perfectly fine. Performance is the everyday price you pay for perfection.
So, if this is so expensive, but sometimes we really need it, what kinds of systems can actually provide linearization? And how on earth do they do it? Well, it all comes down to a process for getting a bunch of computers to agree.
This table gives us a quick cheat sheet. A system with a single leader can, with a lot of care, pull it off. But multi-leader or leaderless systems? Nope, probably not. They're actually designed to allow for conflicts. To get linearizability in a way that can actually survive failures, you need the special sauce, a consensus algorithm.
And consensus is, well, it's pretty much exactly what it sounds like. It is a formal, mathematically proven process that lets a group of computers reliably agree on a single value, even if some of them crash or the network gets flaky. It's the absolute bedrock that makes fault-tolerant linearizability even possible.
Okay, we've covered a ton of ground here. Eventual consistency, linearizability, replication, consensus. So let's bring it all home and reveal the one fundamental idea that connects all of these things.
The big secret, the thing that ties everything together, is order. The entire challenge boils down to this one question. Can all the computers in a system agree on a single definite sequence of events? Because if they can agree on the order, then linearizability is possible. You know which write happened last, you can stop conflicts before they start, you can give every single user a consistent, correct view of the world. In the world of distributed systems, getting consensus on the order of things is everything.
So, let's end this right back where we started, with that quote. Every single app on your phone, every website you use, is constantly making this choice between being perfectly right and simply being alive and responsive. So which path do you think they choose most often? And what does that choice tell us about what we as users really value in our digital lives? Is it perfect correctness, or is it just having things available right now?